In this video, we will discuss the celebrity face recognition system. Convolutional neural network architectures are very powerful at classifying images, and sometimes they even outperform humans. In our final project, we use CNN models to build a facial recognition system, and we also measure the general performance of every model we use. We downloaded the celebrity image dataset from Kaggle website. For further reference, the link to the dataset can be found in the description. The original dataset contains 10,770 images for 100 persons, and each image is 299 by 299 pixels with 3 RGB channels. However, for our purpose, we have reduced the number of classes to 25, and each class has 100 image datasets. The train test validation ratio is 70 to 15 to 15. So from 100 data points, we have 70 training, 15 validation, and 15 test examples. We did most of our training on Google Colab, which is a free cloud service and supports free GPU. Using Google Colab has significantly sped up our training process. In our project, our aim is to build a recognition system that will uniquely identify and verify the identity of a person based on their facial features. Our model is simple, and its main aim is to learn how to use transfer learning in practice and to compare the performance of transfer learning models with regular CNN models. The pre-processing step included data augmentation and normalization. We resized all the image to 224 by 224 pixels, and also we introduced a random horizontal flip in order to avoid overfitting. The batch size is 4. Similarly, the value of the number of workers parameter, which can be found in PyTorch, is 4. Hence, when the current batch has finished, the next batch will be pre-processed and is ready for use. The regular CNN architecture we adopted is called AlexNet. We copied the layer architecture and trained our dataset from scratch with randomly initialized weights. We use this architecture mainly because it's mentioned in Andrew Yuan's video, and we thought it would be fun to actually implement it. For our datasets, the training took a while, and we needed to tune the learning rates in order to achieve a reasonable increase in accuracy. The accuracy of the training dataset, as you can see from the second plot, increases continuously. However, the validation set doesn't show that much change after the initial increase. Hence, we stopped the training process early on to avoid further overfitting. Also, as it can be seen from this first plot, the loss of the validation set is fluctuating, whereas the training loss is still decreasing even if it's very slow. Here we are visualizing random pictures from the validation set. As you can see from the pictures and their prediction label, the prediction is not accurate. Hence, to increase our prediction accuracy, in our next step, we use transfer learning models without pre-trained weights to further train the image dataset. Transfer learning is a machine learning technique where a model trained on one task is repurposed on a second related task. Transfer learning has many advantages. It can speed up training, improve the performance of deep learning models. It can also save computational power. This approach is effective because the transfer models we're using were originally trained on a large image dataset, and also the number of classes in the output layer were relatively large. In turn, the deep layers of the transfer models we're using can already detect complex features very effectively. In comparison, our dataset is very small. It only has 25 classes, and for each class there are 100 elements. Hence, using pre-trained models, we can improve the performance of the dataset prediction variously.
These are the three transfer learning models that we've used. So the first model, VGG16, is a convolutional neural network architecture named after the visual geometric group from Oxford. It makes the improvement over AlexNet by replacing large kernel size filters with multiple 3x3 kernel size filters one after another. It is better because multiple non-linear layers increases the depth of the network, which enables it to learn more complex features. The model is very large, which is also one of the reasons that we have to use transfer learning. And with pre-trained parameters, the training time is around 21 minutes for our model, and the best validation accuracy is around 82%. The second model we use is ResNet. It allows training of deep networks by constructing the network through models called residual models as shown in the figure. Deep networks are hard to train because of the vanishing gradient problems. As gradient is backpropagated to earlier layers, repeated multiplication may make the gradient infinitely small. And the core idea of ResNet is introducing a so-called identity shortcut connection that skips one or more layers. ResNet achieves better accuracy than VGG, and it is also more computationally efficient. For our model, it only takes around 6 minutes to train, and it can achieve 94% validation accuracy. The third model we use is DenseNet. It is similar to ResNet. It further explores the effects of shortcuts connections and connects all layers directly with each other. The inputs of each layer consists of the feature maps of all early layers, and its output is passed to each subsequent layers. The best validation accuracy we get with this network is similar to ResNet. However, the average training time for DenseNet is much longer. As for optimizer, we decided to use stochastic gradient descent. We have experimented on a few options. While stochastic gradient descent gives the best result, the loss decreases fast and also the accuracy is high. These are the test accuracy we get from the four models we've trained on. ResNet and DenseNet's results are quite similar. They both reached around 93% accuracy, and we think this is a quite satisfying result. While between these two networks, we think ResNet is more ideal because it takes much less training time compared to DenseNet. For future improvement, first, this time we only use part of the images from the dataset because we don't have enough time to train on all the images. So next step, we will train on more data. And second, we will use other transfer learning models, for example, inception model. And third, we will fine-tune hyperparameters. And fourth, now we are only using the last layer to train our dataset, and all the rest layers are frozen. So in the future, we want to try freezing only first few of the layers and train on more layers after that with more data.